Hello and welcome to lecture number 12 of ITEC4017 Photo and Non-Photorealistic Rendering. I'm your instructor as always, Leslie Eisted, and today is the last lecture of the class. So we're going to introduce a few new topics, just some wrap up for non-photorealistic rendering, and then we're going to review all of the different topics that we've covered throughout this course and discuss some of the major outcomes that you should have had from participating in this class. So hopefully that'll be interesting. Just remember that assignment 5 is posted and that its due date is approaching. If you're having any trouble running StippleGen, please let me know and I will do my best to assist you with it. And also the final project is posted, and I really, as I want to stress again, that you should take a look at it as soon as possible, because some of the images that we're asking you to render are actually going to take a little bit of time. So take a good look at that now, so you can plan appropriately. All right then, let's dive in to our final topics then. So we left off in our last lecture talking about stroke-based painterly rendering. And this is a fairly big area when it comes to non-photorealistic rendering. There are many, many different algorithms. The algorithms that we introduced you to in your last lecture are actually from 1998. But they are the basis for many newer algorithms, and it's a fairly simple algorithm to understand. So I thought that was a great introduction to the topic. But just to review kind of how they work, the idea is we want to simulate a human painting. And the observation was that humans, when they are painting, they make multiple layers of progressive refinement with smaller and smaller brush strokes. Now that may not be true for every painting style, but for many it is. So we wanted to mimic that by having a virtual painting created with progressive refinement layers, strokes going from really big ones to really skinny ones. Now, of course, a human can look at the page or the canvas and they know exactly where the stroke needs to go, because in their mind, they know what it is they are trying to paint, and they know, okay, I need to put a stroke here because I need to see this color, or I need to have this contour in this particular place. But a computer doesn't know these things. So in our painterly rendering algorithm, we had to identify where strokes were actually needed. And we did that by computing the error between the painting that we have created so far and the input image that we're trying to convert into a painting. And when we find, if the amount of error is exceeding some threshold, that would mean that we need to put a stroke of paint there. And if it's less than the threshold, then the amount of detail is sufficient for that region. Now, if you find you need to place a stroke, you have to find a place in that region in which to start the stroke. And there are many approaches that you can take. A common approach, however, is to choose the pixel which corresponds to the largest error, because that's where presumably you need to make the biggest change. And you will use the color of that particular pixel to make that change or to start the strokes. Now, once you've figured out where to start the strokes, you need to figure out where does the paint stroke go. And again, this is something that a human does very easily, because they are, they know what they're doing. Let's see, random items on my desk. This card that says cat, if I was painting this, I know that I would want to paint the edges, and then on the inside I might want to paint, on a 45-degree angle or something like that. Computer doesn't know what direction the strokes need to go because it doesn't know what it's painting. It doesn't have any understanding. So we have to find some mathematical means by which to direct those strokes. And what we chose to do is compute the gradient field, which seems like a rather complicated idea, but really the gradient field is just describing what direction is the greatest change in color or the greatest change in luminance. Now, the truth is, if you go with the greatest change, they follow the gradient field, you would be crossing all of the edges. So we actually don't want that. However, if you go perpendicular, that is at a 90-degree angle to the gradient field, you would be following the direction of least change, which means you would be following the contours and staying within the object that you are trying to depict. So we follow the perpendicular of the gradient field to direct the strokes around the face. One of the ways that you can think of this is that the gradient field almost could be rendered like a mesh. And we want to paint where there's the least amount of change in the mesh's surface. So I don't want to go down this way. I want to go across here. And the gradient field tells us this direction. And if we take the perpendicular to the gradient field, it tells me this direction, the direction of least change. Now, the method can be parameterized, and it is parameterized with a large number of different parameters, from the number of brushes you're going to use, the size of each of those brushes. There are things like, do you want to exaggerate the strokes, the tolerance, i.e. how much will you consider to be an error before you put a new stroke down. There are a lot of different parameters we can use to customize the algorithm, and due to that customizability, we can actually create a large number of different styles with the same piece of code. So, for example, we were able to create Impressionist, Expressionist, Pointillism, and with just a tiny modification to the algorithm itself, we were even able to create gesture drawings. And how we managed to achieve that was, at the same time as we create the painting's going to tell us where the strokes go. We take those points that we rendered the strokes with, and instead of rendering them as nice big paint strokes, render them as pencil strokes in a second image. And that gave us the drawing, which was actually a pretty clever way of doing it. So just to remind you of some of the things that we were able to achieve with that method, this would be one of them. And you can see here the strokes aren't particularly long, but it creates a nice effect. In these two paintings here, this one on the left, we've chosen to paint on a black canvas. So anything that is near, and we've increased the threshold for error quite high, so that anything that is remotely near black won't get painted, which gives us this kind of neat effect. And then we've rendered with points, so we get this neat pointillist painting. Now, a very similar thing has been done to the painting on the right. And if you're wondering, what is this a painting of? It's a painting of a slot canyon out in Utah. And the difference that we've done here is you'll notice that the points are actually quite far apart. And that's actually something that you can do within the algorithm, is that you can set the minimum spacing between the strokes. And that can create this neat kind of sparse effect. And then this one here, we used really, really long strokes. So we forced the strokes to have a long minimum and maximum length. And then you'll notice here that there's a lot of variation in the color in the painting of this rose that you know probably did not exist in the input photograph, and that's because it didn't. What we did here is we applied an amount of jitter, that is, we added a random value to the stroke color, the paint color, to create kind of a little bit of variation. Because if you look at any of the Impressionist paintings by Monet, you'll observe that there isn't really a lot of solid color blocks, because he's trying to play around with how light is interacting with the various surfaces in the scene. So we can kind of do the same thing here by adding just random values to our paint colors. You get a pretty cool result. And then, of course, this was when we take the same algorithm and make a few modifications to it to produce this gesture drawing. And we've also, so we've got the nice outlines of the rows, and then we managed to get hatching out of the same algorithm as well. And the big change that we did for this was, instead of following the perpendicular of the image gradient, so instead of going with the direction of least change, we went the direction of most change. And that gave us this really cool effect here. Now, that's all fine, but stroke-based painterly rendering is very limited. For example, if you look at this Picasso painting called Girl with a Mandolin, yeah, painterly rendering can't do that. For various reasons. It can't paint this image because there's a lot of distortions to the actual content of the image itself. Like, this is a girl with a mandolin, and I mean, I can vaguely represent, yeah, there's a girl here, and there's a musical instrument, which I'm assuming is a mandolin. But this is not how we would represent a girl typically. This is a very stylized and distorted appearance. And our painterly rendering algorithm is only able to take a look at where do I need to place the stroke and in what direction. It doesn't actually perform any distortions of the input content, which means, yeah, you can't do this. Similarly, things like the Fauvist works, other various abstract styles, you just cannot do them with painterly rendering. The other thing is painterly rendering doesn't produce precise contour drawings. So the contours we were rendering back in Houdini, which are quite precise, very clean and crisp lines, you don't get that from a painterly rendering algorithm. You also don't get things like tune shading, which means that for each of these different styles that you want to create, you're going to need a completely different algorithm, i.e. a different program. That's unfortunate. Or do you? So, a lot of research in the area of non-photorealistic rendering has kind of tapered off in the last 7 or so years, and there's actually a reason for that. So, because we recognize the fact that at the moment, we would be needing a completely different program for each of the different styles we want to render, and that's a bit of a pain. We've recognized the fact that what we really want is one algorithm to rule them all. We want there to be one program where I bring in my input photo and I tell it what style I want, and it just produces it. And I don't have to open another program or do anything else. And furthermore, wouldn't it be interesting if you could tell it what style you wanted by providing it with a sample, instead of having some kind of pre-computed, oh, these are the only styles we support. No, I want to give you a new style, and I want you to figure out what the style is, and I want you, the computer, to apply it to my image. That'd be great. And that is what style transfer is. Style transfer is a singular algorithm, which the idea is you provide it with an input image, and here's one from Monument Valley, and you provide it with a sample painting which represents the style you would like your photo to be in at the end. And this one algorithm is going to learn the style from the sample image and apply it to your photo. And hopefully, that's what you get. And by the way, this is the output of a style transfer algorithm. This is not me running this through a painterly rendering algorithm. This is a style transfer sample. And it's a really good one. If you go back, we can look at these images from, most of you, I'm sure, are familiar with Starry Night by Van Gogh. There are a lot of very visible medium-length brushstrokes. They are following the contours of the hills and various shapes. There are some variation in the blues. We can see what the strokes look like here. There's some swirly strokes. And if you look at how they were applied to this image here, it looks pretty great. Now, sure, we didn't get the big phenomenal swirls in the sky like you get here, but I'm still really, really happy with this result. Okay, so you showed me one style. Well, now let's go back to the example of the girl with the mandolin, this cubist painting by Picasso. I want to take my Monument Valley image and I want to turn it into this painting here, or at least the style of this painting. So I'm going to feed these two images into a style transfer algorithm, and keep in mind, I don't tell it this is a cubist painting. I just provide the image. And this is the result that we get out. Now, this is not quite what I wanted. I was hoping that there would be some additional distortions along the shape of the actual monument. We didn't get that. But we do get some of the background cubey shapes. We have a lot of the colors, and you see a lot of the stroke directions are very much inspired by this painting here. It's not a great result, but it's pretty good. It's decent. The thing I want to point out is that the code that produced this image here is identical to the code that produced this image here. We can take this one step further. Let's try another sample input. So this is, I'm just trying to remember which painting this is. This is a watercolor by Cézanne. It's a self-portrait of himself. And I want to have this monument rendered in the same style. So there we go. I input them into the style transfer algorithm, and this is what I get as an output. Again, I'm actually pretty happy with this. There's a little bit of noise in the sky, which is kind of weird, but I'm not actually that offended by it. But the actual rendition of the monument and the field, I really like. I think this worked really, really well. And again, the code that produced this image is the same as the code that produced this image and this one. It's not some big if block. If this is Monet, produce this. If this is Cubism, do this. It's one piece of code, and it does not know anything about the style that you have given it. This is style transfer. Now, if you're curious to try this out, and in fact, on your final assignment, that's part of the things that we've asked you to do, is to actually do some style transfer examples. I actually used this URL here to produce all of the style transfer images in this lecture. You can do, I think, 5 per day for free. And there's various ways that you can earn extra tokens to do more. There are other various websites on the internet where you can do style transfer, but I have actually found this one to be the best. Some of the other ones are really questionable. So all you have to do to produce these drawings exactly as I have them is to select an input image, select your style image, and hit generate. That's it. There are parameters. I think a Night Cafes has like a strength for stylization, like how much like this style do you want it to be. And I have that set to maximum, and I think that's the default behavior. Some other applications might give you a little extra parameters. They're not necessary. I'm just letting you know they might exist. So there you go. That's style transfer. Seems crazy that you can pass a piece of code, 2 images, and say, make this one look like that one. And it can figure it out and actually make this work. So how is this even working? So the general algorithm, its goal is to extract the style of one and apply it to the other. But it's tricky because you don't want the final image to look too much like the input image. You actually want it to embody the style that you're creating, but you also don't want the output image to look too much like the style image you provide it with, because if you're trying to paint a picture of the monument and you're trying to stylize it with a sample photo of a bunch of giraffes, you probably don't want the giraffes, the content of the style image, to present itself in the painting. So this is an interesting balance that actually exists in style transfer. But how this works is through something called, the algorithm is actually called neural style transfer. And the reason why it's called neural style transfer is because it uses a neural network. And if you've not heard the term before, I'd like to give you just kind of a brief idea as to what a neural network is, what we use them for, what they're made out of, because regardless of where you go from this course, it's terminology that's starting to come up more and more and more, even in places like the visual effects industry and rendering. For example, NVIDIA, for their denoising algorithm, they're not using something for real-time ray tracing. They're not using something simple anymore, like median filter or bilateral filters. They're actually using deep learning, which means they're using deep neural networks to intelligently denoise the image. So these terms, these ideas are coming up all over the place now because we're finding more and more applications of them. So what a neural network is you can kind of think of it as we're trying to create a computational model of how the human brain works. So a neural network, more clearly, is a network of artificial neurons, neurons being, the things in your brain. And we use these typically for some artificial intelligence algorithms. And what an artificial neuron is it's a really simple construct. You've got some number of inputs. It could be one input, it could be two input. And the neuron itself is going to combine these inputs together in some way. Now the inputs are typically assigned weights. So it would be like 20% of this one and 20% of this one and 60% of this other one. But the weights aren't typically pre-specified. Let's deal with that later. Now a lot of times the neuron will just sum the weighted inputs. And then it has something known as an activation function. And if you think about this in terms of the human brain, it's like, I think they call it action potential. I haven't taken biology in like 20 years. But the idea is you have a buildup that reaches a certain threshold. When the threshold is passed, the neuron fires. And if the threshold is not passed, the neuron does not fire. In an artificial neuron, we have an activation function. And there are many different activation functions. They're typically nonlinear in nature. So it's not like yes or no. But one way you could think of it is if the activation function may indicate that the neuron fires and maybe produces a 1. And if it doesn't fire, it might produce a 0. And then what we do is we take all these artificial neurons and we put them together into a network that has layers. And you have an input layer which takes inputs from the user, and an output layer which produces your final result. And then in the middle, you have all these hidden layers of neurons you don't really see. And the idea is this network here should let us achieve some different tasks. And there's many, many different tasks that we might ask a neural network to do. We can use neural networks for classifications. That is, wow. Let's take some more objects off my desk. I'm trying to teach my son to read, so I have all these, letter and word cards. So I've got a whole bunch of cards, and each of these cards is different color. But let's suppose I would like the computer to sort these cards in some way. Then classification would be the labeling of the cards. So it might label them by color, or we could label them according to, is this a letter? Is it a letter? Or is it a word? So classification is labeling the data set. And when I first learned about classification, it was, is this a salmon or a halibut? That's what you're trying to teach the computer. How do you figure out if it's a salmon or a halibut? Then there's another kind of neural network we use for regression. That probably sounds like a complicated idea, but it's really about predicting values. So let's suppose you were looking at the weather, and you have all of these data points for the previous day's weather, and how do you predict the next day's weather? Based on, things like the air currents and the thickness of the clouds and the speed of the wind and, the position of the sun. How do you predict the weather? So one thing you could do is use regression to try to predict those values. And then we can also use neural networks for data processing. So that's things like, instead of telling the computer, there are two groups I want. I want a group of salmon and I want a group of halibut. You sort them. You figure it out. Data processing and clustering is like saying, I'm not sure what groupings exist in this data set. Can you tell me what groupings there are? So then the neural network would look at things like, okay, well, I see that these cards are all different colors. So I could group them by color. That's one way I could group them. Or the computer could say, oh, I see that some of them have more than one letter on them and others only have one letter on them. And so it might group them like that. So there's lots of different tasks that we can achieve via a neural network. And style transfer is one of these things. Now, what's interesting about style transfer is that we're going to be using the network in a slightly different way than what we would for the previous ideas. So what we're also going to use a very specific kind of neural network. Typically for style transfer, we see convolutional neural networks, or CNNs, being used. And it's a big word. We'll explain it simply here. The idea behind this is that, so convolutional neural networks are commonly used for image-based tasks. And the reason for that is because this kind of neural network is going to take the input data and it's going to pass it through these filters where it subdivides the input into smaller and smaller pieces. So it cuts it into small pieces, it may cut those into small pieces, pool those results together, and then cut them and cut them and cut them into smaller pieces. And then it passes the pieces through all those hidden layers to keep extracting these subsamples. And what it's doing by cutting and subdividing is it's actually trying to extract and identify features from the input on its own. And with an image, the idea is when you cut it into small pieces and cut it into small pieces and pool it together and cut it into small pieces, you are looking at smaller and smaller features of the input image. So I'm going to use my daughter's drawing here as an example. But she made me this sign for my desk, which essentially says, "Don't eat or drink near my computer." But if I were to do a convolutional neural network here, I might divide this into 4. And then I might divide each of those into 4. And then I start realizing that some of the pieces have arcs, curves in them, and other pieces have straight lines in them. So I'm extracting curve features and I'm extracting linear features. So that's pretty neat. And the idea is that that's going to help us with things like recognizing, is this a face? Because I'm going to be looking for particular features to exist in the face. And if I find them and they're in a certain proportion to each other, I'm going to be like, oh, I recognize that as being a face. So the idea is that the convolutional neural network is trying to simulate, in a way, how the human visual system works by trying to identify features and then label or categorize them. So Most neural networks, like CNNs, or any kind of artificially intelligent algorithm that uses machine learning, you usually have to train them. And what it means to train something is you are passing a labeled data set into the algorithm. So for example, I would be passing, this big handful of cards. The ones that are see-through are green, obviously. And I'm going to pass this into my neural network to start with, and they're going to be pre-labeled. So this one would be labeled letter, word, word, letter. That's fun. And the idea is it's going to iterate, passing the data through the system and learning what weights it needs to apply to each of the different inputs for each of the different artificial neurons, such that you get the right answer out the other side when you say, is this a letter or a word? So the training is going to initialize the neural network with all of the internal values it needs in order to capture the information that you're trying to capture. Now, it's an iterative process, and the idea is that you're going to keep iterating. There will be a loss function, and that means how close are you to correct. And the idea is you are going to make changes that you think make sense, trying to minimize the loss function, that is, trying to make it more accurate. And once your iterations are making the system no more accurate, the system is converged and it can't do any better. So you stop, and there's your trained neural network, which you can then pass a completely different set of data and ask it to classify or perform whatever task it is you're doing. Now, style transfer uses a convolutional neural network, but it doesn't exactly do any training. This is kind of neat. At least it's not training in the traditional sense. So what you're going to do, or how style transfer algorithms typically work, is the input image, i.e. the photograph, is going to be passed through the network first during what you might consider the training phase. And what happens from there is that it identifies features and figures out what the content of the image is by extracting the various bits and pieces at different levels. It's going to set up some of the weightings and things like that. The next time you run it, well, you're not going to run it. This is going to happen automatically. The style image gets passed through. It's not going to be making any changes. It's going to then be iteratively optimized. And what you're going to do is you're passing the style image through is you're going to try to, your loss function is trying to minimize the balance between content and style. So you want to check, and instead of updating the weights in the neural network so that you get a better output, you're going to leave the weights the same and adjust the image, the output image. So you're going to apply bits of the style image to the content you previously extracted. And the loss function is trying to balance the error in the content reproduction and the error in the style reproduction. Because if the content error is really high, then all you get is style. And if I'm trying to paint Monument Valley using, say, the picture on this can as my style, I don't want it to be painted as a dragon fruit and an orange. There's no dragon fruits or oranges in Monument Valley. I just want the style, the finer details. And the other issue is that if the style error is high, then you get only content. So you have to balance out the errors in this loss function. And it's not like 50%. It doesn't have to be that. The idea is, after you've run the style image through, and it's going to execute this, breaking it up and breaking it up and breaking it up, and adjusting the output image, computing the loss function, and it's going to keep making these updates and updates and updates and making little changes until no more changes happen, or the amount of change happening is minimal, and then you get your final picture. And I know this is probably very difficult to visualize what's happening here. The way that you can kind of think of this is, I'm going to take little pieces from this style image as it's broken them down, and I'm going to find whatever little piece is best suited for this particular region of the content. And then I'm going to put it there. But I don't know what the best is, so I find a little piece and I put it there. And then I compute the error, the loss function. I'm like, let's try again. Then I'll take a different piece and a different piece. And I keep putting pieces of the style image into my painting until I've minimized that loss function. You can almost think of it, another way to think of it is, you're trying to produce a mosaic and you keep reaching into a bucket to pull out a different piece of glass to put there. You don't like that one, so you take it out. Then you reach back into the bag and you put another one, and you don't like that one, and you take it out. And then the one where you stop, you're going to keep, when you stop making progress, you go back to the last one where you didn't like the result, and that becomes your final image for that little square. Now, generally speaking, this method works pretty good. I mean, you saw these images before. They were very happy. We kind of liked them. Look at this. This is a pretty good watercolor painting, and it's way, way simpler and easier to use than the non-photorealistic watercolor painting algorithms I've seen. And this produces a beautiful Van Gogh rendition of this. Does it always work? I mean, here we were kind of iffy. So, let's try some different ones. Monument Valley again, and a gesture drawing. Notice the long, messy strokes that are rendering this flower. And they kind of scribble and go all over. They're very fluid, very loose, really rough. Can we capture that style and transfer it to this picture? That's some pretty demonic lightning. No, we can't. This didn't work. These strokes are not fluid. They're not long. They don't even really look like strokes, to be quite honest. It kind of looks more like a tea egg, the pattern you'd get on a tea egg you've seen, or like a cracked tile that hasn't been washed in a long time. It didn't work, or it didn't work well enough. Why? Well, part of the reason why this did not work well enough was because when we are doing convolutional neural network, we're breaking the image down into little pieces, trying to extract the features. One of the problems of trying to extract the features from this image is that the features are actually kind of part of the content of the image. These strokes represent the style, but they also represent the content. They're quite large. And when we take little pieces of them, it doesn't capture the fluidity of these lines. It doesn't capture that whole arm drawing you would expect. It doesn't work. I mean, it's kind of a weird looking drawing. Let's try another one. So here we have Monument Valley again. And now we want to stylize it in the form of Matisse's La Danse. Okay. This should be fairly easy. Large blocked colors and some black outlines, and not really much for strokes. I mean, they're there-ish, but I don't imagine this painting has a lot of texture to it. I don't think I've actually seen this in person. Okay, let's run it through. It is a very interesting rendition of Monument Valley with arms, legs, and butts. It rendered the picture with body parts and pieces of grass in the sky. Every time I look at this result, it makes me laugh. This is what I'd call an epic failure. This is not what I had in mind. This is not what I expected. And yet, this is what you get. And it's hilarious. I think it's absolutely hilarious. But this is not what we wanted. I was expecting it to be like, okay, well, this is a solid colored sky, and I see large solid colored regions, so I'll just paint it solid colored, and here's another solid colored region, and we'll paint it. Well, it's not that solid, but we'll paint it that. We'll put some black outs. I got nothing that I expected out of this. And I think it comes down to, if you were to subdivide this up into a little bunch of features, you get a bunch of blue squares, a bunch of green squares, a bunch of pink squares. I don't really think there's much features that can be extracted here in a meaningful way using the CNN. So, it didn't work. But it's funny. It's really, really funny. I really do think part of the fun part of assignment 5 and playing with style transfer is see what you can get. I mean, it does a really good job sometimes. And sometimes you get a drawing made of butts. And feet. And arms and legs. I mean, it's an abstract piece, but it's just not what we're going for.
Hello, I'd like to introduce myself. My name is Maury. 7 years old.
And what do you think of this painting?
Silly.
Yeah, there you have it. All right. So style transfer does fail. And when it fails, it can fail pretty epically. So, where does it fail? So, if the style has too much distortion, such as the Cubist drawings, you don't generally see the distortion being exhibited on the content of the input image. And the reason for that is that we want to, in the loss function, we're balancing differences in content and style, and we want to make sure that the loss function is set up such that you don't lose the content. And the problem with trying to take a photo and turn it into a Cubist painting is that you need to lose the content, actually. So interesting questions come up with, can we adjust the loss function to try to recreate more of the distortion? But my instinct says if we try to do that, then we end up with just, the mandolin in the middle of the picture, which doesn't make any sense either. So we may need to, as researchers, take a little bit of a closer look into that. Another place where style transfer tends not to do well is when you have features that are actually content. So those really long, loose, flowing strokes, whether they're paint strokes or sketch strokes or gesture lines, they are just too big to be captured, and they're too much of a content element, and this cannot distinguish between content elements that are both content and style. So it generally works really well if there's not a lot of distortion and the strokes are not too large, because if they're too big, then you're going to risk losing them. And if they're nice and small, then you'll be able to capture them quite easily. So style transfer, it can do a lot of things, but it can't do everything yet. All right. So we've spent a little bit of time talking about non-photorealistic rendering with 3D scenes, but we've spent most of our time actually talking about non-photorealistic rendering in terms of actually manipulating an image itself, which is traditionally where you see it. But certainly non-photorealistic rendering of a 3D scene is actually something that is used. But the styles that tend to be used for that kind of thing are kind of limited, actually. And one place I have seen a fair bit of NPR rendering is games. And maybe you've played some games that were toon shaded. And to be honest, that's a low-hanging fruit in terms of, by that I mean it's easy, it's really easy to do, to give your game a certain look and feel. So you see it in a lot of games, they'll utilize toon shading. But there are some other games which have a painterly look or a watercolor look, but they're much more rare. Now, why would a game engage in using shaders like this? Well, because it creates an interesting storytelling element. For example, this game here, which is called Okami, and it's an older game. I think it's at least 10 years old. I never played it, and to be fair, I think this is somebody's adapted rendering of it. But this game is rendered like a sumi-e painting, which is a Japanese watercolor painting. It's, of course, a Japanese story-themed game. And it's quite beautiful, and this game has been quite revered over the years for its stylization. So this is a shader here. If we were to take a close look at it, you can see that it's as if we have done some toon shading because we've quantized the colors, although there is also some small gradients here. And then we have exaggerated contour lines. But in addition to the contour lines being exaggerated, they are also not nice smooth curves. They're actually quite choppy, and you can see it almost looks like strokes. So that would have to be built into the shader as well, and you can imagine there's quite a bit of code involved in that. Other things, if you look really closely, there's almost a sense of transparency about this, of course, because watercolors are a very transparent paint, unlike oils, which, okay, oils are technically transparent, some of them are, but watercolors, they're all transparent. So this is a really cool looking game. This is another one that used non-photorealistic rendering as part of the story. Now, I've never actually played this game. Actually, I haven't played any of these games. But I certainly heard about them when they came out. So this is called The Unfinished Swan. And it's kind of cool. Like, you start out in this, like, white world. And then it's like you have a paintball gun that shoots black paint. And as you shoot paint at things, parts of the world start to come to life in this stenciled black and white. And I think as you progress in the game, you get like different paint abilities, and so the world starts to take more and more color and more shape. But it's a really interesting style that they created to produce this game. And there's others, but there's not games like this that use the style as part of the story. It's not that common. It can be quite difficult to produce these unique styles. Obviously they can be done, but it takes work. All of the non-photorealistic rendering that you typically see, though, in a game is done by shaders. And of course, because they are shaders, there's programmable units of the rendering pipeline, you can pretty much do anything that you can imagine. And so let's talk about one. And now at the beginning of the term, I asked if there was any styles anything you would like to see. And someone mentioned pixel stylization, pixel art stylization. So it's a 3D game, but it has like it looks like pixel art. So there's a lot of different approaches that you can take to this. We've already showed you how to do this in image space. It's really easy to do in image space. You subdivide your image into a grid, and then each of your grid squares, you compute the average or the median color for the square, and that becomes the new color of the square. Now that's going to give you a large range of colors, so if you want to really take it into 8-bit mode or a pixel art mode, then you need to reduce the colors down to 8 bits, like the traditional 8-bit palette, and then you're going to have to map your colors over to that palette. It's pretty quick. It's pretty easy to do. But how do you do this in a game with 3D geometry? Now, I want to say there are a lot of different ways to do this. This was actually something I've never done before. I thought about how I would do it, and I was successful in doing it, but I was curious, how do other people do it? And I looked it up on YouTube, and there was a lot of different ways to do this. So certainly I encourage you to go on YouTube, and we'll share some links for how to do this in the tutorial slides, of course. But this is just one way of doing it. So the idea is, if we're trying to render pixel art, we want to render things as little squares. So how do I not have a piece of pixel art here? That's not right. Let's find an 8-bit drawing. I'm going to go for 8-bit Zelda. So let's go over here. I'll bring this over here. So this is kind of the style we want. Except we want to take a 3D object and turn it into cubes like this. So we call these voxels. It's a common graphics term. So I want to render my 3D object as voxels. How do we do that? So you can do it. The idea that I had is you're going to need to place some seed positions. So take your geometry, and you need to place some seed positions. Now, one idea that I had was to use the vertices of the mesh as the seeds. Now, the problem with doing that is that the vertices are not evenly spaced. And so if you're trying to use them as seed positions to render a cube at each of those positions, since they're not evenly spaced, the cubes are going to overlap. It's not going to look that nice. So another approach that you can do is your mesh describes a volume, and you could place seeds evenly spaced inside that volume. And then the idea, of course, is that you render a cube with the appropriate scale at each of those seed positions. So I took this into Houdini, and you can do this in Blender, and you can do this in Unity, you can do this. It's just what the shader graph looks like is going to be a little bit different. So this is done actually in Houdini. And we're doing this inside of the torus object. So if we double click on the torus node and go inside, and then we're actually manipulating the torus points. So I'm going to tell you that this top node, this is the actual torus points where all the geometry is actually stored. And we have these two here, these attributes. These are things like position, rotation, and so on. We're going to grab them, but we don't actually need them for rendering the cubes themselves. That's more for the stylization of the cubes. We're not going to use that right now. The important one for this job is points from volume. The points from volume node, what it's going to do is take your volume and distribute a bunch of seed points inside of it that are evenly spaced, uniformly spaced. And if you look at points from volume, they don't actually have to be uniformly spaced. You can do it randomly, but I have set it to uniform. And I've set the point separation parameter to 0.1 because that's how big, I have a really small torus, and so I wanted to make sure it was actually rendered with enough cubes. So I set the point separation to 0.1, and keep that in mind because when we are rendering the cubes, we're going to need to copy that scale into it because we want to make sure that the separation between the points matches the size of the cubes. So if you wanted the points to be non-uniformly distributed, then this jitter seed and jitter scale would be the values that you want to use. But I want them to be uniformly distributed. So the next thing I need is a box. I need to know what geometry do I want to render at each of those points. So I created a box, because I want boxes. And I set the uniform scale of the box to be equal to the separation between the points I placed into the volume. So I set it to 0.1, again, because my torus is really small. I tend to do things really small in Houdini. I don't know why. Now, what I have now is this copy 2 points. So the second input is the points I want to copy that are going to have the thing copied to. And the first input is the thing I want to copy onto the points. So I want to put a box on each of those volume points. So I use copy to points to put a box on each of those points. And then I grab the attributes transfer so that I can transfer the attributes of this onto my boxes. Okay, what do we get? That's what I get. I turned my torus into a bunch of little cubes. And there's 0. Well, you can see here, it's a really small torus because that's the 1 unit. And it looks pretty cool, right? And we can ray trace it. And here I actually applied a tuned shader to it. Now, this is just the default tuned shader. I have not actually, so I've built this shader to turn the geometry into a bunch of cubes, the pixel appearance. But the one thing that I didn't do is I didn't adjust the shading. So you can see here that the highlight actually has an arc to it, and that some of the cubes are partially shaded in one color and partially in another. And if we were talking about true pixel art or voxel art, then we would actually want this to be aligned with the cube. So if the cube is in the highlight, it should be 100% highlight on that face. You can modify the tune shader to do that though. And that part I'm going to leave for the tutorial. One of the links that I have for you should give you all of the information that you need in order to do that. So it's pretty cool. Now you could have rendered this with smaller boxes, and to do smaller boxes, then all you had to do was adjust the point separation to a smaller value and the cube size to a smaller value. And similarly, if you wanted bigger cubes, then make it bigger, larger separation, larger cube size. Now here's one interesting thing. You know, there's our voxel art. It's really easy to do, actually. What if I don't want boxes? Okay. So use spheres. So this is the exact same piece shader with one tiny change. And instead of having the box node here, I just put a sphere. And you get a torus of spheres. And I think that looks pretty cool. I like that. Or you could have a torus made of tori. And again, all I have to do is go back to here, swap out the box for a different piece of geometry. So if you wanted to make a teapot of teapots, you could do that. If you want to make a dragon made of teapots, you could do that. If you wanted to make a torus made out of dragons, you could do that. If you're using the dragon model that I provided, you might have a little problem with that. Because it's a really big model. I don't recommend that one. The point I'm trying to make, though, is that this technique lets you copy any kind of geometry onto those points. And you can have a lot of fun with it. All right. So, what do we do now? We've talked about a lot of different non-photorealistic rendering algorithms, And I want to end our section on non-photorealistic rendering with talking about NPR from the perspective of how do you do it for stereoscopic 3D. If you remember back in the photorealistic rendering, we kind of wrapped that up with a discussion of how do you do stereo rendering for photoreal. So I want to do that here as well. So we know that rendering a 2D image is really easy. You take your photo, you apply your filter, and you render, and you're done. Does that translate to stereo 3D? What do I mean by stereo 3D? So we need to have a little bit of a better understanding of the stereo 3D aspect before we can really discuss how do we do this, or can we just do this for apply filters to 3D. So if you remember, stereo 3D is the human visual system's ability to take two images and interpret depth from them. You get one image for each eye, and what's interesting about them is the images are slightly different. And they're slightly different because, of course, your eyes are separated by a small horizontal distance called the interocular, and so they're slightly different cameras into the world. So they're slightly different images. And if you don't believe me, I mean, there's a very simple experiment that you can do. What I want you to do then, if you want to see this separation for yourself, close one of your eyes and then hold your arm out like this and use your thumb to cover something in the distance. So there's a thumbtack on the wall behind me, and I'm going to do that. And then without moving, swap your eyes. And whatever object your thumb was covering, you'll note that it's not covering anymore. And that's because your eye you just switched to is in a different position, and therefore it can see around what your thumb was covering. So it's pretty neat. That separation is interpreted by your brain as depth. But in order for it to do that, it needs to be able to identify, oh, look, there's that object, there's that edge there in this eye, and oh, I found it in the other signal. And when it can match those two signals together, it then takes the separation and takes them as depth. Keep that in mind. That's a really important idea, that your brain has to find the matching pieces in the two images. So we need two images to do stereo image. We need one for your left eye and one for your right eye. Seems pretty easy, right? So you're just going to render two shots of the scene. Or take two images and then stylize them. Say, oh, I want to apply painterly rendering, so I've got my left and right views, and I'll just push this one through and push that one through, right? Is that all we need to do? Sounds like that's all we need to do. So just an example here of separation. This is an avatar shot. If you take a really close look at this image, you'll actually see that, parts of the image are only visible in one of them, and that's due to the horizontal separation. This is a ray traced image from my own private ray tracer, which I built a stereo camera for. And again, you can see that each view sees a slightly different take on the world. In particular, some of the books are, these wood blocks are only visible in the left image and they're not visible in the right. And at the same time, there's parts of the wallpaper that are only visible in the right that are not visible in the left. So you can see slightly different advantages of the scene. Now, if we were doing this in a 3D game engine or in Houdini, dealing with the stereo camera is so easy because you either just place two cameras in the scene and render them, or you're going to place a stereo camera in the scene and it's going to automatically render that. That should be enough. Now you do have to be careful about randomization. We'll explain that in a bit. We're going to focus on doing non-photorealistic rendering for stereo 3D in image space because for game engines it's actually really straightforward. So here's the problem. If the image is rendered differently in the left and right, then your brain's not going to be able to fuse the images. That means it's not going to be able to find the matching thing in your other eye, which means it doesn't know what to do with it, and it can cause you either discomfort It can give you double vision, actually. Or it can do something called binocular rivalry, which is where the brain is trying to fuse it, and it ends up rapidly switching back and forth between the two images. And I personally don't know what that experience is like, because it's not something that's possible for me to experience, but I've heard it's quite unsettling and uncomfortable. So this is something to keep in mind when it comes to non-photorealistic rendering. We have to make sure that however the object is rendered in the left image is rendered the same in the right image. And that isn't generally true when we're playing with stereo cameras in a 3D world like Houdini. So we don't have to worry about it so much here. It's in the image space that we have to worry about, because we can't, we would be passing the image through the algorithm and then passing the second image through the algorithm. So I don't know if you're able to free view, but if you are able to free view, this is actually set up in cross-eyed format. So for cross-eye viewing, so if you're careful, you might be able to try to get a stereo image out of this by crossing your eyes. I'm going to warn you, though, that this one's going to hurt. And it hurts because it's not consistent. The strokes that render this bowling pin in the left are completely different than the strokes that are rendering the bowling pin in the right. Which means when your brain is trying to fuse the left and right images, it can't fuse them because this stroke here doesn't exist over here, and this stroke here doesn't exist over here, so your brain is going to just be like, ow. So this idea of taking the left image, running it through the stylization algorithm, taking the right image and running it through the stylization algorithm doesn't work. And it doesn't work because the algorithm isn't aware that it's two images and they need to be stylized together. I need to know that if the stroke is here, that stroke needs to appear in the appropriate place over here. And running them separately through the algorithm, it just doesn't work. And here's an example where it really doesn't work. So this is the stained glass, or no, I guess this is Mosaic from, I think it's from Photoshop. It might be from GIMP, I don't remember. No, it is Photoshop. Because I'm about to show you an algorithm I developed while I was working at Adobe Research. So this, you can see here, there's this blue pane here. There's a blue one up here. Again, you're welcome to try to do cross-eyed viewing of this, but I'm warning you, it's going to hurt because they just don't match at all. So it's very clear if we want to do stylization of a 3D image that we need to be doing it in such a way that if I place a stroke or a tile here, I need to find the matching part in the other image and place the same tile or same stroke there. And there actually are algorithms that do this. What they do is they take the left image and they stylize it, and then they do what's known as a stereo warp to map that image to the right. And you do that using the depth or disparity map. You can actually warp all the pixels to the other one. The problem with that particular technique is that the stuff that's in the left is only a subset of the stuff that's visible in the right. So you'll have a bunch of blank areas in the right image that you then have to stylize and add those. And the risk is that at the boundaries of where you stylize from left and right, you'll end up with strokes or content that's going to cause some visual discomfort and confusion. So the method I'm about to tell you for doing this is actually my method. And this is what we wanted to do. We wanted to guarantee that the stylization as it were applied is identical in the left and right image. So if I put a stroke here, I want that exact same stroke to be in the other image. And I want it guaranteed. Now, I had this idea because I was thinking about how do I see or think about depth, because as some of you know from earlier in the term, I'm what's known as stereo blind. It means my brain does not fuse and interpret depth. 3D movies do nothing. But I was thinking about, what does depth mean to me? And the thought that I had is that it's like an onion, where you've got layers that you can just keep peeling off. And the things that are further away, are on the other side. There's a layer that you got to peel off a whole bunch of others in order to get to. And things that are up close, well, that's on the layer that's on the outside of the onion. And thinking about it that way helped me come up with this idea here. So what we're going to do is we're going to break the stereo image into a bunch of layers by depth. So things that are 1 meter away, things that are 2 meters away, except, disparity we're going to do with pixel depths. What I observed is that if I take, so the background of this picture, which we like to call the creepy baby picture, this is from the Middlebury dataset, is this flat, it's against this map plane. Look at this blue dot that I've placed under this baby doll's arm. And then I've added a pink dot on the other side under the other arm. Now what we notice is that, so that's the left and the right image. They have the same depth. If I cut out those pixels, and only those pixels from left and right at that particular depth, I get 2 images. And I can take them, and if I slide them like this, I can actually make them line up perfectly, as you can see in this image here. And you can see the blue dot from the left image and the blue dot from the right image. What this image here is a merged depth layer. This is everything that you can see at that furthest away depth. And you can actually decompose the stereo image into layers by depth like this and create merged layers. The idea then, so this is kind of what a merged layer looks like. So the original left image, it goes from the left edge to some area over here, and then the right image is from the right over. And everything in the middle is perfectly overlapping pixels. The pink area is only visible to the left, and the blue area is only visible to the right. That's what your merged depth layer looks like. And this whole layer contains only pixels from that depth. So there's nothing from the foreground, this would be only just the background, if this was the background layer. To give you another example of what this looks like, so this is a mask that shows you the pixels that are visible at this particular depth in the left. I guess that's the right. This one is the left. And if I take these 2 images and I merge them together, I can now see everything at that particular depth. So I now know everything that's visible in the scene at that depth. Now, why did I decompose it? We're going to apply the stylization to the merged layer. We need to guarantee that how the stroke presents itself in the left is identical to how it presents itself in the right, without any warpings or distortions. And the best way to do that is to apply it to these merged layers. Because these are both, the merged layers actually represent the left and the right at that depth. So we apply the stylization to the merged layer. And then what you're going to do is you cut the left and right image back out of it after stylization. So going back to slide 53, this image here, so you take your merged layer, you cut from the left to this dotted line to get your left image, and then to get your right image, you cut from the right to this dotted line. Now you've got your left and right. Because the left and right came from the same image, you've guaranteed that the stylization for that depth is identical in both, even if the position in the image is different. You do this to each of your layers, and then you composite them all back together, and you have a stylized image that is guaranteed to be consistent. And so now we have this painterly result. Now, admittedly, there's a tiny change that was made to the painterly rendering algorithm that is used here. So because we had depth information and we want the strokes to be following the objects really nicely, we actually told the stroke, we took the depth information and added that in to the image gradient to encourage the strokes to actually follow the shape of the objects and the patterns. So it's this tiny modification to the algorithm from before. And if you look at it, let's look at this pink rendering here. There's a long pink stroke right here. There's that long pink stroke right there. Little pink stroke there, little pink stroke there. Now, some of the strokes might be in slightly different positions because they're at different depths. So the separation is going to be a little different. But the stroke is there, and it's rendered the same. Guaranteed, consistent, all the time. And for many styles, this works great. So it works great for painterly rendering. So this is a really fun one that we did. This, we actually, instead of stylizing it for some kind of non-photorealistic rendering algorithm, this one here, we created artificial depth of field. So this was actually an image that was 100% in focus, and we just applied a different Gaussian blur to each layer. Approaching the focal area, we made the blur less and less and less. So applied depth of field artificially. Looks pretty good. And then this is, I think, one of the pencil crayon-like styles from Photoshop's filter gallery. Again, we applied the technique in the same order. Guaranteed consistency. That's pretty neat. Does it always work? No. It always guarantees consistency. That is just the way the algorithm works. But does not work for every style, unfortunately. So we have found that if you want to do any kind of contour-based stylization, it does not work. And the reason for that is the contours, when you subdivide the image into a bunch of layers, you get contours for the content on each of the layers because you've effectively broken the object up into a whole bunch of sub-objects. So contour rendering, anything where you want the edges does not really work. But there are other techniques that can be used. So that's pretty cool. So if we can do these things for stereo 3D, the question then becomes, can we do them for virtual reality and augmented reality? That's an interesting question. And sure, you can apply shaders to game engines and 3D worlds. We have to keep a few things in mind. When you're dealing with something like virtual reality, you are actually able to walk around and explore the space. And with augmented reality, the object is actually going to be sitting in your camera view, and you can, look around it as if it's there through your device. So again, you get this sense of exploration. Some of these techniques and non-photorealistic rendering techniques are going to be very simple. Tune shading, straightforward. You're just quantizing the color. It's going to produce a result that's not realistic, but that's what we were going for. And it, a smooth round object is still going to look like a smooth round object, just with a cool lighting scheme now. But if we wanted to do something a little bit more complicated, like painterly rendering, how do you do painterly rendering for virtual and augmented reality? That's a good question, actually. So one of the things to consider is that there's a few approaches we could take. One of the approaches we could take is we could actually do our stylization in a texture that we then apply to the object. So I could, stylize this label for this can in Photoshop or whatever, and then I could save the texture and then just apply it. It technically works. It's very easy to do, and you get complete control over the style because you could just hand paint it even. The unfortunate part of that is that you are wrapping the object with the style. You are creating the appearance of wrapping paper. Now, for something like this can label, if I was to do like a hand-drawn style, that would be fine. But if I were to do something like a painterly render can, that doesn't make sense. Because if you look at most paintings in art galleries, the strokes actually have a physical texture to them. And so when I walk around the object, or I look at the object in my phone, and the strokes, which my brain knows should have some texture and some roughness and some going over the contours of the object, but they're flat on the surface, there's this odd disconnect. It looks like this wrapping paper, and it doesn't look as nice as we want it to. So then you have to ask yourself, well, how would we do stroke rendering for these kinds of 3D scenes, even a 3D game? There are some algorithms out there that instead of you creating the wrapping paper look, they actually create physical strokes around the object, almost like curved labels of their own. The trick there is you want to make sure that the strokes themselves don't become objects in the space that are an interference or a distraction to the user. I mean, I've never actually played around with, I've never put a VR headset on. I wear glasses. I don't know. I know a lot of people wear glasses and then they wear VR headsets. I've never done it. I don't know why. But I can imagine, I've been in these caves, these VR caves, where you can actually physically walk around and you're surrounded by the scenes. And I can't imagine being in like a field of paint strokes. Maybe it creates a cool effect. I don't know. It seems something like you would need to really balance. Maybe that's some interesting research to do. How do you do painterly in VR? Because you don't want to make it wrapping paper, but you may not want the strokes to be too distracting either. And there's many other styles which need some texture added to them where you need to actually be careful about. All right. So what I want to do now, that's the end of the non-photorealistic part. What I want to do now is just do a review of the topics that we've covered and show you some of the major results that we had just to refresh you so that you're well prepared for the different things that we're going to be doing in the final project. So we started out the first half of this course was discussing photorealistic rendering. We looked at ray casting and ray tracing, which are, two parts of kind of the same algorithm. We looked at intersection tests, so how to do a ray triangle intersection and a ray sphere intersection. Now I know unless you are implementing a ray tracer yourself, this is mathematics that you're probably not going to have to do in Houdini. Sometimes we see this in shaders when we want to do a little more complicated idea, but you have the math, you have the resources. We also did transformations between the world space, the viewing space, the model space, and vice versa, because we often want to actually perform our transformations in the model space instead of the world space. Because if I want to rotate my remote so that it's 45 degrees, I want it to do this right here, not literally like move over here 45 degrees. So I want to apply that transformation in the model space, not the world space. We saw some funny examples if you did it in the wrong space. We talked about a large number of rendering and lighting equations for direct illumination. That means point lights, spotlights, and so on. We looked at area lights as well so that we could get hard shadows, soft shadows. We also looked at environment lighting, how to actually compute that. And then we looked at various materials and how light interacts with them. So things like diffuse surfaces and the Lambertian model. We looked at shiny surfaces, so Phong and Blin Phong, which are very simple, but we tend to use Blin Phong because it's faster. It has a few less computations in it. I don't think that matters much today. We looked at textures, so actually applying the labels to objects. We looked at bump mapping, which is an interesting idea where you're keeping the shape of the object, but you're perturbing the normal. So when the light computation is performed, it looks like it's textured, but it actually isn't. We looked at how to do reflections and refractions. So remember our ray casting, it's just from the camera through the pixel into the world. First thing you hit, that's the color of the pixel. Gives you an image like this. There's no shadows, no lighting, solid colors. Ray casting algorithm, however, it's very valuable to know this, because if you're doing any kind of, picking algorithm where you're trying to click on things in the screen, what thing did I click on? Use this as a modification to ray casting. If you are firing arrows into the game, you can use ray casting. It's a very useful algorithm for a large number of topics. Ray tracing was a little bit different, because we actually, from the point of intersection, we sent shadow rays, we sent rays for reflections and refractions. And it gives us far more interesting rendering. Now we see shadows, we actually see the surfaces of the objects. And there's the shadow ray computation model. What's interesting is if there's multiple lights, you're going to send multiple shadow rays. Don't forget that. So this is where we have one light source, and so we get one shadow. When I add a second light source, you'll see we actually get a secondary shadow. You're going to send one shadow ray for each light. And if it's a aerial light or any kind of volumetric light, then you're going to be sending multiple shadow rays. So of course there is our nice crisp hard shadow, which sometimes happens, but not really. This is the kind of shadow you get with a point light source. And then if we change it to an area light, instead of sending a single shadow ray, we send a large number of randomly perturbed shadow rays to positions in the area light. And then we average their findings to get a nice soft shadow. And of course, because we're sending more rays, we talked about how this would actually impact performance. Then there are things like spotlights, area lights, this isn't the area light, this is the environment light. This is bump mapping. Again, this scene is just a plain cube and a plain sphere, and what you can clearly see here is that instead of having a nice smooth lighting, the lighting appears, it makes it look like it's bumpy. It's not actually bumpy, it's just we've pretended it was by perturbing the normal. And you perturb the normal using the bump map, which is an image we use to determine the values we're going to add to the normals. This is some examples from our reflection. And this one in here is very interesting to remember, because one of the things that we can do with ray tracing and with reflections in particular is that, if you're a ray and you hit a reflective surface, you send another ray. And if that ray hits a reflective surface, it would send another ray. And the problem is that you're going to bounce rays around for infinity. So we need to actually put a cap, remember, on the number of reflective rays, or how deep the reflection goes. So this one here has a limit of 10. And we saw in that particular lecture that if you set the limit to smaller values, some of these reflections that we actually see in this scene aren't here. 10 is actually a pretty good number, but it's going to be costly because, of course, now instead of sending one ray, you're sending 10. A lot more work. Then we looked at refraction. Don't forget that surfaces that are transparent, we need to set their index of refraction, which is going to tell us how much the light bends, or what the ray's direction is as it exits the object. And we saw here that things like diamond can actually impact the ray quite a bit, because it bends the light a lot more. So we also looked at, so those were the very straightforward lighting and surface models. We looked at subsurface scattering. That's where light is bouncing around on the just under the skin of the surface, quite literally. And then it might be reflected from the surface from a different point other than its entry, or it might get absorbed. We looked at BRDFs, which are ways of describing the probability that light is reflected in each direction off of a surface. So for example, with Lambertian, we see that the light, or a diffuse surface, the probability of the light being reflected in any direction is equal. The amount of light reflected in each direction is also generally equal. We looked at methods to improve rendering quality by increasing the number of rays. We also looked at rendering performance, counting how many different ray and object intersection tests we were actually going to end up doing. And then we looked at things like oct trees and KD trees and bounding volumes in order to reduce the search space of the ray. And those are standard techniques that you can customize in most of your major rendering tools like Houdini and Arnold and so on. So just to remind you of what these different features look like, here's our lovely subsurface scattering where we're able to make things look like they're glowing. Interesting enough, before we actually had methods for doing subsurface scattering, skin looked awful when it was rendered. I mean, this is one of the problems with photorealistic rendering of organic objects, is that we have really poor models of how light interacts with things like skin and hair, and so it creates this uncanny appearance. But once subsurface scattering became a thing, we noticed a huge improvement in the rendering of organic objects. It's still not great, but we're getting a lot better. A lot better. So a lot of people confuse subsurface scattering with transparency. So of course this is the dragon rendered with partial transparency. I think this was set to 0.5. So you can see here that it does look like it's glowing, but it also looks like a foggy glass. When we do subsurface scattering, we don't actually see straight through the object like we are here. We're seeing straight through the object to the light. This thick part of the dragon's body we don't see through because it's so thick. But the part, we get around it, the thin parts, that's where we start to see through the light through it, and it creates that glow. Now we said quality. So this is what happens when you send 1 ray per pixel. It's all grainy. And if we up it to 25, this is the same result. This is the result that you get. And you can see here there is a notable improvement in the quality and the smoothness of the rendering. If you want something really high quality, you're going to want to send 100 rays per pixel. A lot of rays. You can send more than that. It's going to take a really long time, but you can send more than that. After we covered those topics on direct illumination, we also took a look at indirect illumination or global illumination as a more accurate solution to the rendering equation. We looked at the radiosity algorithm, and that was for diffuse surfaces. We looked at caustics. That is where you have something like this glass of juice, and the shiny surface, light hits it, reflects off of it, and lights up something else and creates these neat bright spots. We have path tracing algorithms, which are tracing the light in reverse from the camera back into the world to see what it captured, and photon mapping, which traced the light from the light into the world. We also looked at spectral rendering, which is a more accurate way of doing rendering because we know that the different wavelengths of light are going to certainly bend differently as they pass through certain objects. So spectral rendering, we have rays for each wavelength or groups of wavelengths. So let's look at some of the major results that we saw. So this is a radiosity result, and you'll notice that it's very patchy because that's exactly how the radiosity algorithm worked. We subdivide all of the objects into a bunch of rectangular patches, and then we're asking each patch, what can you see? And we iterate until we make no more changes or changes less than a threshold, and then we're like, yeah, now we like it. The problem, of course, is that you end up with this blocky result, which you then have to interpolate and smooth out. The path tracing algorithm, just to remind you, so if this is the screen plane here and this is the camera, we trace the light to the surface of the object, and then we're going to send many rays into the world in directions and probabilities according to the BRDF of the surface of that object. And then we're going to aggregate all those results back together to figure out what the final, and that's the gather stage. We gather the results of all of the rays we fired to figure out what the final color should be at this point. Whereas photon mapping, we sent a whole bunch of photons, rays, from the light sources into the scene and to see what did they touch, and once they intersected with an object, where would that photon have been reflected, and how much of that photon's energy would have been reflected with it, because obviously some of these objects are going to absorb some of that energy. And then what happens is when you ray trace, you're going to look up information from the photon map to determine exactly what the lighting at that particular point should be. So we can take this, which has direct only illumination, and when we add radiosity, you get this lovely result where we know that some of the light is going to reflect red off of the red wall and blue off of the blue wall. And this, again, is direct illumination only, and we used to think this looked pretty good, and then we realized when we added indirect illumination that our glass looked really boring. And now it looks better because we have caustics, the indirect illumination sources. And the same here with this scene. We know that shiny objects like gold should be reflecting light into the world, and that light should be actually lighting up some of the objects. So when we turn global illumination on here, you can see many different caustic effects in this particular image, lighting up other areas of the scene. We combined caustics and our global illumination with spectral rendering or dispersion, and it gave us a bit of an improvement on our rendering of something like a diamond, which is notoriously difficult to render because of its high index of refraction. It's hard to photograph a diamond too. So this was the result we get. Now we have caustics where we've got a bunch of the indirect lighting, and we've got the rainbow separation because we have the dispersion going on as well. Still not a very good rendered diamond though. After we talked about all of those global illumination algorithms, then we actually moved on and talked a little bit about shaders and the rendering pipeline. Now, we didn't spend a lot of time on this because a lot of the different shaders are actually implementing different sub-algorithms that you would see in ray tracing or ray casting. So the rendering pipeline is what you would see in Houdini. Well, if you turned off ray tracing, it's what you see in Unity. It's what you see in game engines. It's an alternative to ray tracing. It's also known as rasterization. And the idea is the rendering pipeline, you have this big pipeline, and there's various components within it that are programmable. And so you have things like vertex shaders where you can manipulate the color of a vertex and the position of a vertex. You have geometry shaders where you can turn one vertex into 100 or 100 into 1. And then we have fragment or pixel shaders where we can actually compute the final color or appearance of a small fragment that's going to be turned onto this screen. One of the other big differences between rasterization versus ray tracing is that a lot of rasterization algorithms, game engines, you're doing this in real time. So it's much, much, much faster. And yet, more and more, we're seeing a lot of ray tracing and casting elements becoming a part of these shaders. So this here, we did in Houdini, and this is where we're making use of a displacement mapping. So this is where I have an image, and instead of perturbing the normals, I actually perturbed the geometry. So in this case, you rendered this with micropolygons. So I have a shader here that is going to take the few polygons that this sphere was made out of, and it's going to turn it into some that are like sub-pixel size. And then we use displacement mapping as a shader to manipulate the position of those vertices and actually give the sphere a texture that if you reached out and you were to touch it, you'd actually feel it. Whereas when we did it with bump mapping, you could see it, but you couldn't touch it. Of course, you can go really crazy with displacement mapping, whereas you can't really do that with bump mapping. We looked at a few shader graphs in Houdini and how we can manipulate things like the color computations to create unique looks. So here it's a displacement based on a noise function and a transparency as well. And then this one here, I have added more vertices, performed a displacement, and I have a texture transparency. So these shaders, while many shaders are written in languages like C and Python, you can actually do this with node networks, as we've seen throughout the course, to give you whatever custom look you want. Now, we covered photorealistic rendering first because a lot of the ideas that we built there, we manipulated in our non-photorealistic rendering part. So first we covered basic filters, things like median, box, and Gaussian filters, which are used for denoising and also sometimes used for applying a blur. We looked at combinations of these algorithms that could be used to create some really simple, fast looks. We looked at toon shading and contours, so things to make it look like it's a cartoon. And we found that actually you can make things look like a cartoon by manipulating the lighting equation. And it was as simple as mapping the angle. So we're going to take the angle between the normal and the light and map that to a texture coordinate, and the texture coordinate is a lookup into a texture ramp, which tells us which color the final pixel should be. And in image space, of course, we did toon shading via quantization, that is reducing the total number of colors we see in the screen. We looked at hatching and stippling and pen and ink in screen space, but also on 3D models, where we generated hatches along geodesic lines, lines that go around the arcs. We also did stippled diagrams using weighted Voronoi method. And that was really cool because we did this crazy math diagram. We created it using a bunch of cones, which is such a cool thing. I remember when I learned that, and I was like, no way. People used very basic computer graphic rendering to create this math diagram. It was so cool. Maybe you don't get as excited about it as I do, but I thought it was really cool. I still think it's cool. So here, this is a filter from Photoshop. This is actually where we have computed the edges using a Sobel filter. And this is where we've combined things. So we've combined here a denoising algorithm with the edges that we found to create almost a cartoonish look, although we haven't quantized the color. We created the toon look in Houdini as well, so as in our 3D models, using texture ramps. And we quantized the colors. Now in image space. Now if you remember, when we originally quantized the colors, we found that noise in image space was a pretty big problem. So we found that when you apply a median filter or a bilateral filter, which preserves the edges, you get a much cleaner result when you apply toon shading to the image space. For contours, they were much, much easier to do in 3D because we actually have the 3D information. And we manipulated, in this case, the lighting equation, the angle between the view vector and the light. And the view and the normal. And wherever that was equal to 0, then we found that that was turning away from the viewer and therefore should be the contours. So really, really simple manipulation of some of the lighting equations give us cool things like contours. These are some of the results you might remember from our Voronoi stippling, where we use that cool Voronoi diagram to actually place the stipples in the image with uniform distance according to the darkness of our input. And that was really fun. And that's on assignment 5, playing around with StippleGen. We looked, of course, at painterly rendering, so how to render something with a bunch of strokes, how to place the strokes, where to place the strokes, where you need refinement. We looked at style transfer and stereo 3D. So there's a whole range of topics. And the hope here is that when you walk away from this course after the final project, that you'll have a much better understanding of what's going on with ray tracing under the hood. That's really useful if you're trying to create realistic images, because you need to be able to understand what are the tools I need in order to produce the look I want. What are the kinds of lights I'm going to need? What are the kinds of materials? Do I need direct or indirect approaches to lighting? We talked a lot about the shader pipeline and how to do vertex geometry and fragment shaders, and that's going to help you too with rendering as well. We're hoping that you walk away with this course for the basic understanding and knowledge about simple filters for denoising and edge finding, also style transfer, where it works and when it doesn't. We're also hoping that you'll be able to reproduce some of these simple non-photorealistic shaders and think about how can I manipulate that rendering equation to give this a unique appearance. Hopefully, this has been a fun course for you. I know this is a topic that I love talking about, so I hope you have enjoyed it. Just as an end note, please make sure you fill out the formal course review. I think you should have received an email about it, but I'm not sure. The other thing is, if there's any feedback that you'd like to convey, by all means, please send an email, fire a message off on Discord. My goal is always to make sure that the courses that I put forward are interesting, exciting, and a little bit challenging, and of course fun. So if you have any feedback, please share it. And please get started on your final projects. I know I keep banging on that same drum, but they're going to take a while to render. So you might want to get started. If you need any server time for your rendering, please let me know. We have a little bit of rendering power, so we can pass to you. So if you need it, let us know and we can pass that on. So I hope this has been fun. This is your last lecture. There is a tutorial that will be posted for tomorrow, and we will see you when you submit your final projects.